Okay, let's kick off now. Good afternoon to everybody. My name is Alejandro Falcon, CIBSE UAE Events Organizer and Social Secretary, and I welcome you this afternoon on our CIBSE webinar, Refrigerant Safety in Buildings. CIBSE responsibility in the region is to promote the intellectual welfare of its members and improve the understanding of building services engineering within our society, and by organizing events and other activities related to the built environment. The agenda for today will start with a brief on upcoming CIBSE event, a speaker introduction, a speaker agenda, session notes, a speaker presentation, a Q&A session, membership, and close out. Stay tuned. We are going to be having on 26th of August a very interesting CIBSE virtual conference on healthy buildings. It's going to be online and from 2 p.m. to 5 p.m. And just to give you a brief on the topics that are going to be covered, there will be an opening presentation by International Wellbeing Institute, followed by a presentation by Riva Golf Chapter. There will be also a panel on the role of sustainability and energy efficiency in promoting healthy buildings post-COVID-19 world. Presentation on transforming spaces, co-working and co-living, flexibility and adaptability. Impact of poor terminal units, design on thermal comfort and occupant health with a case study. Another panel discussion on evaluating the current landscape of MEP sector in promoting future healthy buildings. Finally, a presentation on HVAC recommendations for occupation after COVID-19 lockdown, how to safely operate buildings based on the latest recommendation from the ASHRAE. It's going to be a nice one. Really try not to miss it out. Our speaker of the day is Dr. Jason Shilliday. He's the Regional Sales Manager of MSA. He has a PhD in Environmental Technology from Brunel University, London. He has over 15 years experience in the HVAC and refrigeration industries in Europe and the Middle East, working in design, contracting, manufacturing, and is a specialist in refrigeration gas detection. Established in 1914, MSA Safety Incorporated is the global leader in development, manufacture, and supply of safety products that protect people and facility infrastructures. The company's comprehensive product line is used by workers around the world in a broad range of markets, including the oil, gas, petrochemical industry, the fire service, the construction industry, mining, and the military. MSA core products include self-contained breathing apparatus, fixed gas and flame detection systems, portable gas detection instruments, industrial head protection products, fire and rescue helmets, and fall protection devices. Jason is going to walk us today through history of refrigerant gases and environmental concerns surrounding their use, advantage of the new refrigerant, hydrofluoroolefin blends. He's going to walk us through EN, ISO, and ASHRAE standard and guidelines on refrigerant safety in buildings, BREAM and LEED, building VRF systems and refrigerant safety design, safe design of machine plant rooms and district cooling plants, detecting leaks of refrigerant, gas sensor technology. Please, once I open the panel of Q&A session, write your question down there, and by the end of the presentation, those will be answered by the speaker. Your camera will be off and you will be muted. So without further delay, I give way to our speaker, Jason Shilliday. So Jason, whenever you want, please kindly share your screen and go ahead.
Thank you, Alejandro. Thanks very much to CIBSE for inviting me to present. I'll just share my screen. Okay, so today we're going to talk about refrigerant safety in buildings. MSA is a US manufacturer of gas detection systems, and we also have a range of refrigerant detection systems. So that's what we're going to cover today, how to make our buildings with refrigerant safe. So Alejandro has went over the agenda, so we'll just get straight into refrigeration systems. So there really is two kinds of refrigeration systems. We have the indirect systems, which chill water, and then the water is circulated around the building. So this is, it's used for cooling, comfort cooling in buildings and for district cooling. And then we also have the direct system. So our DX, our splits, and our VRF, where the gas is actually circulated itself around the building. So it's not exchanged to water. So the gas can leak into the building. So this is used for comfort cooling, for food processing, and for pharmaceuticals. So refrigerants can either be natural refrigerants, such as ammonia or propane, carbon dioxide, or they can be synthetic. So the synthetic ones are manufactured with the correct pressure and temperature relationships to generate cooling or heating effect. The synthetic ones generally have poor warning properties, so they don't have any smell. They're generally safe, but there is an asphyxiation risk if a leak occurs. So if a leak was to occur, the person wouldn't be breathing in oxygen, they'd be breathing in refrigeration gas, which can be a risk. So a large leak can cause an immediate danger to life or health due to a low oxygen atmosphere. There's also costly implications in Europe and the US, and soon to be in the Middle East, due to this refrigerant, as prices are going up, and there can be fines as well due to the regulations. The gases are also highly global warming. There's been recent changes in regulation to limit the amount of gas on sale due to this. And then leaks also cause systems to operate inefficiently, so that they consume more electricity due to these leaks. So there have been some fatalities and injuries due to refrigeration leaks, over the course of the last 100 years. A lot of them to do with ammonia and propane, but there also has been some due to HFO or HFC leaks, mostly due to asphyxiation. People are breathing in the refrigeration gas and not getting enough oxygen. The prices of refrigerant globally can range from about $15 to $100 per kilogram, depending on where you are in the world. So if you have two large chillers, water-cooled chillers for an office building, a large leak could cost anywhere from $15,000 to $100,000. So this is why owners are looking for leak detection, to know when their chillers are leaking. If the system does start leaking, you also need to have a recovery process. So you need to shut down the chiller to recover the gas and charge it again. So this is a loss of productivity and cooling for the end user. Plus, if they lose cooling for the frozen foods or pharmaceuticals, it can be very costly, as that batch of drugs or that batch of foods will probably have to be thrown out. This table gives you a brief overview of the history of refrigerants. So in the 1990s, the first refrigerants invented were chlorofluorocarbons way back in the 1970s, but these were they were very highly ozone depleting. So in the Montreal Protocol, they were actually banned. So the first ones were R11, R12, and R500. So newer ones, HCFCs, were brought out. So they were slightly lower. They were lower ODP, lower ozone depletion potential. They were R22 and R123. And they were banned. So the new refrigerants were brought out, such as HFCs. There was no chlorine atom in them. So they were R134A, 410A, and R407C. But it was discovered they were highly global warming. So they had a high GWP. So the Kyoto Protocol was signed to start phasing them down. So modern refrigerants have a lower global warming potential, such as some of the HFCs or the more modern HFOs. But the HFOs have brought in other complexities because they are slightly flammable. So all the refrigerants before this, they weren't flammable. They were relatively safe, but the more modern ones now are becoming flammable. So this is leading a lot of owners and operators to look at natural refrigerants again. So they're looking at propane, ammonia, and carbon dioxide, which were the first refrigerants, and looking to use them again to stop using synthetic refrigerants. So refrigerants are classified in ASHRAE 34 and EN 378, depending on the toxicity of the gas and the flammability of the gas. So a non-flammable gas would have a 1 rating, mildly flammable 2L, and then up to a higher flammable gas such as propane would be 3. And then we have the toxicity, which is A or B, depending on if it's toxic below 400 ppm. Most gases that we're dealing with in buildings are A1. So this is all the 134As, but the new gases are coming into a new category, which is A2L. So such as the R1234 and R32 are in this category. So it's something to consider when you're designing buildings and trying to select the gas. Is that gas flammable and is that gas toxic? So we can see here a table of a lot of the gases. The gases really have changed throughout the years. The early gas, R12, which was highly ozone depleting, was changed down to R22, which is much lower ozone depleting. It was also lower global warming, but because of the Montreal Protocol, it was banned. So some of the new gases, R404A and 134A, were non-ozone depleting, but you can see here the GWP started to increase. So gases were synthetic. You started to mix them into certain blends. So you can see here our 404A, which was a blend for multiple temperature ranges, was a mixture of many different gases. And then 410A, which is used in VRF, it also is highly global warming too. So there is a lot of it being changed to R32, but you can see here that it is in that A2L category, which is mildly flammable. Another part in this table which we should consider is the allowable concentration. So this is the safe concentration of refrigerant allowed in a room. So we'll go through the standards in EN 378 and ASHRAE, but it mainly looks at how much gas could escape into a room. So the room is not allowed to go above this concentration. We can also see on this table some of the more new refrigerants, such as 134ZE. The main benefit of it is its very low GWP. So it's future-proofing the refrigerant, but it has a lower flammability limit, which needs to be considered when designing the refrigeration system and the plant room. So I think Carrier is using this refrigerant and Trane is using our 1233. Each manufacturer has their own gas they prefer to use. So it's important to look at this table and to look at the ASHRAE 34 and EN 378 standards to see how each of the gases compare to each other. And it's also important to compare the coefficient of performance and energy efficiency of these gases compared to the old gases. The environmental concerns are also something people are talking about. So the Montreal Protocol banned the ozone depleting gases and it set a timeline for developing countries in the Middle East. Then the Kyoto Protocol phased out the highly global warming gases. The European F-gas regulations, they're much more stringent on the GWP. So they've actually set a ban on gases with a GWP of over 2,500 in 2020. And then this actually is reduced down to 150 in 2030. So you can see why a lot of manufacturers and a lot of end users are changing to gases with a much lower GWP, and compressor manufacturers are manufacturing compressors which are able to generate good coefficient of performance with these new gases. One important factor also in the F-gas regulations is that, automatic leak detection is required if the installation has a 500 tons of CO2 equivalent in its system. So to calculate the tons of CO2 equivalent, you just multiply it by the GWP of the gas. So that's the equivalent figure in carbon dioxide if it was released into the atmosphere. There's also financial concerns with these gases. The gases have increased dramatically in price in Europe due to a quota system. So you're not allowed, the governments have not allowed imports of HFCs, which has put less of the gases, the harmful gases on the market, which has had a dramatic price increase, up to 700% increase in some of the gases. So you can see here our 404A is a higher GWP than 134A. So the price has went up much more steeply. So the early detection of these leaks will save the end user a lot of money when they have to recharge with these gases. A lot of the end users are also taking these highly polluting gases out and putting in new, more modern gases. So the early detection of these leaks is important to the end users to save money and to save efficiency in the system. So the Quota System actually wants to phase down to 21% of the consumption of HFCs in Europe by 2030. So they're limiting the amount of these gases that are actually available in the market. So hence the steep increase in the price. So now we're going to take a quick look at the standards to do with refrigeration system safety. So the standards are, we have EN 378, which is used in Europe. We have ASHRAE 15 and ASHRAE 34, which is used in the USA. The Middle East uses a combination of these standards. And then we have the ISO 5149, which is the international standard, which actually leads quite a lot into EN 378 and some of the Australian standards. So these standards apply to any refrigeration system. So chillers, the whole chiller installation, VRF, split systems, and then commercial cooling and industrial systems as well. So we always recommend that you apply the most suitable standard to do with the occupied space, and then comply with local government regulations as well. So EN 378, this is the British version of EN 378. So each partner in Europe would have a different version. The Germans would have a DIN version. So it classifies the type of refrigeration system. So as we discussed in the first slide, is it a direct system or is it an indirect system? Then it classifies the access category to how safe the building is if there was a leak. So it's a general access, which it would have more safety. Is it a school or a hotel? And then you have authorized access areas, so non-public areas such as plant rooms, where you would be allowed more gas in those areas. It shows you how to calculate the volume of gas and then how much gas is actually allowed in the system. And then it sets the safety requirements that are required, whether it's leak detection, safety shutoff valves, the maximum charge, or ventilation requirements. Generally, if there's a large leak, we want the ventilation in the plant room to turn on to extract all that refrigerant out. And then we have ASHRAE 15, which is similar in some ways to EN 378. So it also classifies the system. It sets the access category of the occupied space, and then it sets the safety requirements as well. So the standards have a lot of similarities. Then we have the international standard, which EN gets a lot of its content from too. So now we move on to BREAM and what BREAM says about refrigerants and pollutants. So BREAM enables you to gain some points and some credits for different uses of refrigerant in buildings. So if you don't use any refrigerant in the building, you will gain 3 points, 3 credits. If you keep the GWP of the gas and the life cycle of the gas down below 10 and 100, you'll gain 2 credits. And there is a calculator available in BREAM in order to show you how many credits you're able to get from the system. Or you can get 1 credit if you keep the total life cycle of the refrigerant down below 1000, and you get another credit if you add a refrigerant leak detection system and a pump down system. So different buildings will have different complexities, and you won't be able to put a no refrigerant system into all buildings. So it gives you flexibility to gain points with a different type of system that you use. So now we go on to VRF and what VRF what EN 378 says about VRF systems and the occupied spaces. So the risk is in a VRF system that there's a leak into the occupied space from the indoor unit. VRF systems in the Middle East are very big because of the increased cooling capacities required here. So generally there's a lot of gas contained in the outdoor unit and also in the pipes into the indoor unit. So if there is a leak that happens above the ceiling, due to the density of the gas will actually leak down to the floor and then leak upwards. So it's very important that we keep the concentration limit of the gas above what it's meant, below what it's meant to be. So due to these large volumes, they should be checked for EN 378 and ASHRAE compliance to prevent suffocation, asphyxiation of the occupants. So there is maximum limits in the charge that should be applied, or it enables you to use alternative measures such as leak detection or warning systems to be installed. So as I showed you on the first slide, EN 378 gives you a table of the allowable concentration limits depending on the gas that you've used in the system. So this is the maximum concentration limit in kilograms of gas per volume that is allowed. If there's a risk that this concentration limit can get higher, then you need to put in an alternative measure such as safety valves or leak detection. So we just run through an example. So this is a typical hotel room, a typical size, which is about 72 meters cubed. So we know from the VRF manufacturer that there's 50 kilograms of gas in this system for this hotel floor. So we need to see, is this system compliant with EN 378? So we divide the total quantity of gas in the system by the volume of the room in order to get it into kilograms per meters cubed. So once we do that, we have a figure of 0.69, which is greater than the maximum concentration limit allowed in EN 378. So we know in this particular room, to comply with EN 378 and ASHRAE, we need to put in leak detection, or we need to reduce the volume of gas in the system. So a lot of buildings in Europe are putting in much smaller systems in order to comply with this regulation, so they prevent leak detection, they don't need leak detection. So you can either comply by putting leak detection in, or lots of smaller systems spread all over the building. So this is an example of a system in Dubai. It's a school that's under construction. So you can see here, the consultant just specified a typical leak detector in the room. So they actually put leak detectors in every room, but we went through with the consultant and did the calculation according to EN 378, and leak detection wasn't required in every room because the rooms were very big. And these are the typical specs you should be looking for leak detection. As long as you put in your ASHRAE, comply with ASHRAE 15, 2016 or 2019 and the EN 378 standard, then the contractor will have to design appropriately to those standards. Chiller plant rooms is the other large source of refrigerants. So they also need leak detection to comply with ASHRAE 15. So ASHRAE 15 says a gas detector should be located in the machinery room where a leak could concentrate. So generally throughout Dubai, throughout the Middle East, we work very closely with the manufacturers and the consultants, and we design the plant room to house a refrigerant leak detector. So the gas detector then is designed to link into the BMS system. So if a large leak is detected, it actually activates the mechanical ventilation system to extract the leak to make it safe for people to work in that area. So then there's an audible and visual alarm inside the room and then at each doorway as well. EN 378 is similar. You have to calculate. So ASHRAE says you must put in a leak detector, but EN 378 allows you to calculate just as we did before, using the refrigeration concentration limit, and then take the appropriate measure as required, whether it's ventilation, safety shut-up valves, and safety alarm in conjunction with the gas detection device according to the standards. As an example, if we have 3 chillers with approximately 1,000 kilograms of 134A, We know that refrigeration concentration limit is 0.21. So by dividing them, we know the minimum volume of the room required is going to be about 14,000 meters cubed, and that is a huge room. So we know that leak detection will be required in that room in order to comply with EN. The other thing EN says, because the A2L refrigerants, there is a flammability limit. Leak detection is actually required for any charge over 6.48 kilograms. So this applies to, of course, the A2L gases in the table in the first few slides that I showed you. So R1234ZE or R32 in the split. So it's important to consider this when designing VRF systems or water chiller systems with A2L gases. So a typical leak detection system is shown as it is here. So we have a refrigerant monitor, a leak detector on the wall, and it houses, there's a pump inside it that connects to different sampling points around the room. So there's two different types of detection system. We can have separate detectors, or we can have a sampling based system, which sucks air in from around the chillers. And then if it detects gas, it will bring up an alarm. The benefits of a sampling type system is there's only one detector, one sensor that needs to be calibrated. If there's many detectors around the room, these need to be calibrated every year, and they're quite expensive to calibrate. The other thing that ASHRAE says is that you need to have breathing apparatus at the doorway and the entryway signaling as well. This is a typical example of a large plant room. This one was actually in Jeddah Airport, where you can see here we have a typical leak detector and all the tubing going into the bottom of the leak detector, and then the tubing going throughout the room. So the pipes would normally be underground, and they would come up, and we would have a filter at the end. So air would be sampled the whole way around the chiller room, and if a detector picks up a refrigerant in one area, then it would alarm and send a signal to the BMS system. Depending on the size of leak, then it would activate the ventilation or just notify the authorized person. So this was required to be ASHRAE 15 compliant with detection down to 1 part per million. And then there was 6 detectors in total in this building. So just really a final slide on a refrigerant gas detection technology. So the detection technology we use is photoacoustic infrared. So we have a sampling chamber in the detector, and then we have a infrared light source, and we have an optical filter. So the optical filter is set for the particular gas that you're going to monitor. So it's set for that wavelength. So in this case, it's 134A. So we take in a sample of air, and then we shut the air inside the sampling chamber. So you can see here in the second image, some of the gas is coming in. So this is 134A. As the gas is impacted by the infrared light, it starts to vibrate. And those small vibrations are picked up by a very small microphone, which converts these vibrations into a ppm, and then you get that ppm on the screen of the detector. So it's a very accurate way of measuring gas using infrared light, which doesn't fade like other gas detection methods like the semiconductor. Okay. Thanks for your time. You can see my email at the bottom there, so you can get me on email or LinkedIn if you have any questions. Thank you.
Thank you, Jason. Very nice presentation, very interesting. So now let's a little bit read some of the questions that you got here. For the entire audience, please, this is the opportunity for you to ask any questions that you may have. Feel free to write them. It's the time now to get them responded. I will give maybe 1 or 2 more minutes if anyone else wants to add any additional question, and we kick off the Q&A session. Okay, I think we just kick off. There are two questions for you, Jason. The first question is, do we consider just the volume of the gas to the particular indoor unit or full VRF system to decide if a room requires leak detector?
So you have to take the volume of that room, and then you have to take the volume of the refrigerant that's in the entire system. So the manufacturer will, in his design software, have a figure of gas which that system needs to operate, to function. So you take the entire charge of the system, and then you take the volume of the room that the indoor unit is in. So if you have lots of rooms connected to one VRF system, you have to do the calculation 6 or 7 times, depending on how many indoor units you have. But it's important to take the maximum volume of the gas that's in the system.
Okay, I think that's a response that you got, Pradosh. The next question is from Isan. He asked, hi, what is the maximum coverage area of one leak detector?
So the leak detector that we manufacture, leak detector what detects down to 25 ppm. So that's 25 parts of gas in a million parts of air. So generally 1 or maximum 2 leak detectors, it's all that's required in the room. You generally position the detector where the indoor unit is. So if there is a leak, the detector will pick it up. But if the room is very, very large, you're more than likely not required to need an actual leak detector because the volume is very big. So you'll never actually get over that refrigeration concentration limit that's required by EN or ASHRAE.
Okay. Okay, that's your response, Isan, I think it is. This is a question for you, Jason, saying, is there any difference of using refrigerant sensor for chillers that is positive pressure and negative pressure design?
So the chiller, if the chiller, if there's a leak in the piping of the chiller will eventually leak, even though it's negative pressure. So the negative pressure will actually suck in surrounding air and positively pressurize the condenser side of the chiller. So the chiller will eventually leak. You'll also get oil droplets coming out, which have refrigerant contained in them as well. So it doesn't really matter about positive or negative pressure. If there's a leak in the chiller, the refrigerant will come out, and having air sucked into the chiller is extremely bad for the compressor.
Okay, that's the response to the question. There's another question coming. Yeah, that's nothing. Any other one wants to raise any question? Yes, there is something coming here. Is saying, Isan again, do we need to interface with ventilation system if there is any leakage as per NFPA?
NFPA, that would depend on the type of refrigerant in the system. Like these are mostly freons, so if it has an LFL, maybe if it's one of the new gases, one of the A2L, you would need to interlink with the ventilation system. But with ASHRAE and EN378, you need to interlink with the ventilation system anyway. So generally, there's 3 levels of alarm. There's a low, medium, and high. And then on the high alarm, you have full fan speed for the extract. So if you're designing as per ASHRAE, you're interlinked with the ventilation system anyway. Okay,
that makes sense. That's your response.
And EN standards as well. So and EN as well.
Yeah. This worldwide cover. This is another question from Sanush. Sanush is asking, have refrigerants R410A and R134A already been phased out as of now?
134A isn't phased out yet. In the Middle East, it's going to take quite a while to phase them out. So if you're designing buildings, it's maybe appropriate that you look for those lower GWP options for the next 5 or 10 years, because I know that's what's happening in Europe and the US a lot more. The designers and the consultants are looking for gases which are going to be future proof, and that is the gases with the lower GWP. So have a look at the tables in EN 378 and ASHRAE and speak to the manufacturers and see which of the gases has the lowest GWP and the highest performance.
Okay, Jason. There is a question from Mr. Chan here saying, different refrigerants have different operating pressure. How to upgrade our system?
Yeah, so there will be a refrigerant blend, a new refrigerant blend to match an old refrigerant blend. So Honeywell will have a drop-in refrigerant, it's called, and it will match with the oil. You need to also match with the oil type that's in the chiller. So for each of the old gases, there will be a drop-in gas, it's called. If you contact Honeywell, the refrigerant manufacturers.
Okay, that's a response for you, Chan. Then another question is, what is the lifespan for refrigerator sensor?
For the infrared type of sensors, because it's infrared based, it's not reacting with air all the time like a semiconductor or MOS. There's a lifespan of up to 10 years. I have systems working in to Breed and Empower that are they're 8 to 10 years old and they're still going well. As long as you have proper maintenance, and it's important not to get small particles in the filter, in the sensor. So maintenance, and then your system could last up to 10 years. Okay. The other reactive types of MOS or semiconductor sensors will probably last maybe 1 to 2 years.
Okay. I'm reading one more question. It's a little bit longer. Bear with me. Okay. Okay. That's this. Okay. Seems like there is no more additional question from the audience. Jason, thank you very much. Before I proceed with all the slides, I want to thank you so much for your presentation today, for taking your time to putting your slides together and continue to contribute to share knowledge to our UAE community and engineering community. So thank you very much for today. And for the audience, any other questions? I know some people sometimes are, let's say, a little shy to type questions here. So please feel free to address any further questions that may arise later or you don't want to arise here to Jason Shilliday at msasafety.com. So he can, I'm sure he will be more than pleased to respond to your questions.
Thank you very much.
If you time him, yes. So anything you want to add, Jason, before I move on?
No, that's it. Thanks very much for listening, everyone.
Thank you very much, Jason. Thank you very much. I'm sharing now my screen. Yes, I want to take opportunity to have you all guys here to speak a little bit about CIBSE membership. I please encourage you guys to join CIBSE, become members at any grade that is suitable for you, based on your level of advancement of your career, contribution to the industry, perhaps your level of responsibility, position in your organization, whatever it is you feel more comfortable with to join. Just entering cibse.org/membership and find there what is the most suitable degree grade that you can actually use to join CIBSE. Really, I encourage you to do it. Any question that you may have also, we can locally assist you if you write us on UAE@CIBSE.org. Some of the benefits that you can have of being a CIBSE member is full access to our CIBSE journal, applications, and our electronic newsletter. You can enjoy accessing CIBSE guides. We have a comprehensive technical guidance on all of the areas of the MVP services and the industry. You can access to our knowledge portal, training, courses, events. You can access and let's say network with our other CIBSE societies, special interest groups. So I really encourage you guys to, whoever is still not a CIBSE member, just do so. It's really interesting. You participate, you learn a lot, you network with very interesting people. So I really encourage you to do so. So thank you today for joining us. I hope you have actually enjoyed your presentation. Again, if you have any questions, you can address them directly to Jason. If you have any other kind of concern or question that is more related to CIBSE, again, you can reach us on CIBSE.org and write us on UAE@CIBSE.org. You can follow us on LinkedIn. You can follow us on Twitter. And I'll be looking forward to seeing you in our CIBSE virtual conference, Healthy Buildings, on 26 August from 2 to 5 p.m. So thank you very much.